Okay, one more thing this week. So what we're going to do in this last little video, and just the same thing, I'm going to review the PowerPoint. It's not that it's a replacement for the PowerPoint. I'd still like you to go through it. I'm going to just kind of hit the highlights. But for geologic time, our last component is absolute dating method. So here's a way that we can get some numeric values. And the idea is this is how the geologic timescale was created. We use relative dating principles to get kind of a stack and organization. Because we didn't know ages, we used names, right? Cretaceous and Jurassic and things like that. As techniques improved, then we were able to put some numbers on some of these things, and that ultimately led to the geologic timescale with names and numbers. So once again, like, this is an intro class. I'm going to kind of cruise through this stuff pretty quick because I don't want you to get bogged down in the details. This isn't a chemistry class, it's a 101 class, but some background information about absolute age dating. So you can go through this kind of atom stuff, but really what I want you to remember, and you should know just because general knowledge about science, that there are atoms that make up everything, right? We have a periodic table of what we call elements for atoms. Every atom is composed of a nucleus, and there's some particles that compose the nucleus, that's protons and neutrons, and then there's some electrons that kind of orbit around there. So you might have seen the model like the one on the bottom left or even the one on the bottom right is how we kind of visualize it to explain it, though it doesn't exactly look like that. The reason we care is because not all atoms kind of look like this and that they're stable. And so we want to use unstable atoms because that's going to help us with figuring out some ages. Okay, so the thing that to remember when we look at atoms is they have an atomic number. And that atomic number is actually associated with the atom or the element. So in this case, for carbon, there are 6 protons. Every carbon atom must have 6 protons. If you don't have 6 protons, you are not a carbon atom. If you have 1, you're a hydrogen atom. If you have 92, you're a uranium atom. But if you have more or less, you are another element. You're not, a carbon atom anymore if you don't have 6 protons. And that's true of all the elements. So if you look at a periodic table, the number here actually is telling you the number of protons in the nucleus. And so here we have carbon has 6, nitrogen 7, oxygen 8. If you have 7, you are not an oxygen atom, you are a nitrogen atom. Right? So it gives us some information there. So what we want to look at are what are called isotopes. So isotopes are elements that have extra neutrons in their nucleus. Okay, so an example here, there is carbon. So carbon is very abundant, and the most common form is what's called carbon-12. It has 6 protons, 6 neutrons. But we also have some carbon atoms that have extra neutrons in them. These are called isotopes. And these isotopes are unstable. Okay, so they're not happy in the form of having an extra neutron in them. And they spontaneously change or break down. And this change, they release either some protons or some neutrons or some electrons. They can decay in a number of ways. We call this decay radioactivity. And so when we have something like a carbon atom that's carbon-14, it is actually going to decay over time into a nitrogen, right? Because it's unstable in its form, and over time it's going to change into something more stable. Once it reaches that stable form, it stays there and it's happy. Okay, so we can use some different methods here. Of course, you can look through this really fast. I'm going to cruise through that. Some of the terms we want you to be able to understand, and just once again, we're trying to keep it simple here, is that when we have the unstable version, and so not all elements have isotopes, but the ones that we care about, right? When they have the unstable version, we're going to call the parent, and the parent is going to change or decay into something more stable. We're going to call that the daughter product or the daughter element. Okay, and so when we look through something like this, we have this radioactive element. Why? Because it's an isotope, it's got extra neutrons, it's unstable, it decays spontaneously In this case, it's a specific type of decay. It's getting rid of some neutrons and some protons, so it's turning into something else, another atom that I can identify, right? Like carbon going to nitrogen over time or something like that. Now, there's a bunch of decay processes. You don't have to know those, but there's different ways that it can become stable, and these are just some of the common ones, and they're not always super simple. And so you've probably heard of uranium. You know, uranium, certain types are radioactive. Over time, they will decay into lead, but of course, it can be a complicated process. Once again, we're not getting into that. I just want you to be aware that it's not always something super simple. So, what we can use this to our advantage to understand the ages of certain rocks, at least on a very basic level. And the idea is that in this example here, we have parent atoms, so those little square black things with some rocks in it. Those would be the unstable version, the isotope version of an atom. Over time, those atoms will decay. They will change into a more stable version, a daughter product. And so we could see that as time goes on, more and more daughter product is apparent or shows up in my mineral, and less parent atoms show up in my mineral. So the more daughter product there is, the less parent. The older the rock is, because more time has transpired. The longer and older the rock is, the more time it has to decay. So the more accumulated, I hate that word, the more the daughter product accumulates. And so we can use that just to get an overall idea of what's older and what's younger. But we can even be more specific, and we will in just a second. So here's the deal. Does this work on every rock? No. It really works the best, and the one we rely on are igneous rocks. And why is that? It's because in a magma, when the rock is molten, the minerals have, or the atoms have, the ability to move around. And of course, they're attracted to each other, and they bond together and form specific minerals. Now, in the case of these unstable atoms, specific minerals can form that only include the unstable version and none of the stable version. So the idea is that when the mineral first crystallizes and forms, there are no daughter product in that mineral structure, only the parent. And from that point on, once it crystallizes and locks in, it slowly starts to decay, and more daughter product will build up as the rock ages. So the other thing to be aware of is that it's not a linear decay, it's actually an exponential decay. But once again, I don't want to get bogged down in the math or anything like that. We can use that to our advantage. We use something called the half-life. So every system, carbon to nitrogen, uranium to lead, has a specific number called a half-life. And it is exactly what it says here. The time it takes for half of whatever you have at that moment to decay from parent to daughter. And so we give time frames for different systems in half-lives. And so some are short, like carbon to nitrogen, 5,000 and change. Some are really long, like billions of years from uranium to lead. So we use the short ones for young rocks and the longer ones for older rocks. So if you were given a question like this, right, you have two samples here. Both are igneous, so they both can be used to get an absolute age on. If we look at the basalt, it's got 5,000 parents and 5,000 daughter. We look at the rhyolite, 2,500 to 7,500. So which is older and why? Now you can see that together, when we add those up, they both started with the same amount. So the argument would be that, hopefully you were able to figure this out, that the rhyolite is older because there's more daughter product. It's had more time, so the parent is constantly decaying, and as the time span is longer, we have more daughter product than we do parent. And that's all we can get from this, because that's all we know if we're just comparing. As long as you have a general understanding that as time goes on, we get more daughter product and less parent. And that's assuming that we have the same amount as to start with. We can compare that way. Okay? So, if we look at something like this, here's the deal. Because you know that when the rock formed and the mineral that formed in it had 0 daughter, that's the rule that when I look for a sample to get an absolute age on, I'm looking for a specific mineral. That specific mineral I know can only include the unstable version of that atom in its structure. And so I can't just randomly pick a rock that's igneous and say, oh, I'll use that one. Right? I have to have something that's made up of, uranium or strontium, one of the ones that is radioactive, number one, and a specific mineral that I know can only incorporate that unstable one in its structure, so that I know there's no daughter in there. So if that's the truth, that there's no daughter, then every atom that starts out in there is the unstable version. And over time, we see that half of it goes away in a certain period of time we're going to call a half-life. So let's say that you discovered a sample and you counted, put it in a machine, and it counts the number of atoms, daughter and parent. If you count 750 daughter atoms and 250 parent atoms, what that tells you is every daughter atom had to start out as a parent. So if I gave you this and said, here's what you counted in your machine, how old is this rock? What you need to remember is that this first statement is always true. I take all the daughter. Where did they come from? They came from the decay of the parent. So I'm going to take this 750 and add it back into the 250. And I always know my starting point. I must have started with 1,000 parent atoms. And of course, no daughter. And then you just take half of what's here. So half of 1,000 is 500. What happened to the other 500? There they are there. Now, that was one half-life. If I give you what the half-life is for this system, then you can puzzle out its numeric age. But look, if this is what you got, then it had to take 2 half-lives to get to this ratio. And so 1 half-life gave you this, 2 gave you that. So this ratio tells me that 2 half-lives has transpired. Or, of course, we could keep going, right, depending on what you got. So here's the example. So I give you this information, that there was 1,000, right, at the beginning, but today there was only 250. If there's 1,000 parent at the beginning, I know this has to be 0, because that's the rule. And so how do I get to 250? I have to take half. That's 1 half-life. How do I get to 250? I got to take another half-life. So I had to take 2 half-lives to get to the current amount of parent that I measured in my machine today, given that the half-life for this particular system is 100 million years. It took 100 million for half of the parent to decay to here. It took another 100 million to get to here. So this sample must be 200 million years old. You need to remember that this is always true at the beginning. As long as you have the beginning number here, you just go half, 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 and count how many times you took half. And then you're just going to multiply it by the system. If this was 500, it would just be 2 times 500. If this was, 3.2 million, you'd multiply 2 times 3.2 million. And this is the extent that we would like you to be able to understand or calculate an absolute age, okay? And so, given some numbers like this, you would be able to puzzle out how many half-lives took place and then use the number given to tell me the age of the sample, okay? So, there are some parameters that need to happen to get a good age, and one of those is you have to have a closed system. So that means you can't add or subtract anything in there. Metamorphism, bad. And so when we have events that heat and cool the rock or crush the rock, that can cause the parent and daughter ratio to be off. This is why we don't use metamorphic rocks for getting good ages on. And let's see. So, and of course we said, look, here's the deal. Igneous rocks, those are good. Said rocks, not so much, because they're pieces of other rocks. They don't really help us. Metamorphic rocks, they alter some of the numbers. Not good. So we need igneous rocks. And we can't just do random igneous rocks, right? They have to have a specific mineral that I know has the radioactive element in it, and then it hasn't been altered over time. So field geology is super important, right? You need to be able to go out in the field and identify some of the features there and say, nope, can't use that. Yes, I can use that. All right. Let's see. This example is, okay, we'll just blaze through it. You can run through this really fast, but remember, it's saying a wood fragment. So you're using the wood, and which means it's made of carbon, to figure out how old something is. But what you're calculating here, of course, is not the age of the rock. You're calculating the age of the wood. So you just want to be careful. I wouldn't give you a trick question like this, but it is something to think about. That if you find a wood fragment trapped in a sandstone, the wood is a certain age, but the rock could be something different. So we just want to be careful when you're reading the questions like that. All right, so here's the 3 criteria that need to occur for this system to work. You can't have any daughter product in the beginning. We said that. You're going to look at a sample and be able to identify a mineral that would only incorporate the parent into the system. It can't have been altered. And of course, there has to be a measurable amount. So if the mineral has a tiny amount of parent, or if a long period of time has transpired and almost all of the parent has decayed to daughter, it would be hard to count the number of parent atoms. So those 3 things have to occur for us to get an accurate age date. And then, of course, we can use both our relative age knowledge and our absolute age to give us some numbers. Like, I can't get an age on this rock here in the middle because it's a sedimentary rock. But if I know that this lava flow is 400 and this is 200, and their lava flows, remember, so we treat them like sedimentary rocks, then there's a stack, an order. This is older than this, than this. I know that this layer has to be between 200,000 years old and 400,000 years old. And that's much better than having no idea. It's not the best, but we can bracket, and that's what we do when we combine our absolute and relative ages. So if we look at this diagram once again, we can see that if given some numbers here, the order doesn't change. We still could say, yeah, A, B, C, E, D, then F, then G, H, I, J, K. And that's wonderful. But now that I have some other information, I know that, look, this sill came in at 1.1 billion years ago, or 1,100 million years ago, which means that all of A, B, C, and E were already there. So they have to be older than that, right? And that the lava flow occurred at 20 million, which means everything above that has to be younger than 20 million. So look, if you're asked what's the age of I, you can't just tell me it's younger than H. You need to tell me it's younger than 20 million because you have more information. And so if you're asked a question about the age of something, given some numbers, older or younger isn't a complete answer, right? So how old is G? Well, yes, it is older than H, but it is older than 20 million because we have some other information. So make sure that you use that when you're answering questions for quizzes or homework and things like that, right? So here's the deal, right? These layers have to be younger because of the age of H. G is bracketed. Okay, it's a big bracket, but it's more than I had, right? And then, of course, these are older than that. So you want to be able to use that, and that's how we're going to use our absolute age dating. So nothing complicated. You'll be given the number of atoms of parent and daughter, and you just need to figure out how many half-lives has transpired. Remember the rule, you always start out with 0 daughter. So whatever numbers I give you, you add the daughter back to the parent, and that's your starting number. And then you're just going to take half of the parent. What number do you get? Does that match what you calculated today? If it doesn't, you need to keep taking half until the number matches what you measured today. Count how many times you took half, and then multiply it by the half-life given for that system. And then you get a numerical value, and voila, you can use that to add to your relative knowledge and tell a more complete story.